What specific problem does ALPHAONE aim to solve regarding the transition between fast and slow thinking in large reasoning models, LRMs?
ALPHAONE aims to solve the problem of inefficient transitioning between fast and slow thinking in large reasoning models, LRMs, which often struggle with overthinking or underthinking due to their inability to optimally manage the system 1-to-2 reasoning transition. The existing methods, such as sequential scaling, either enforce monotonous patterns of slow thinking or fail to adequately modulate the reasoning process, leading to suboptimal performance. ALPHAONE introduces a universal reasoning progress modulation framework that allows for continuous modulation of slow thinking transitions, enabling LRMs to effectively switch between fast and slow thinking based on a user-defined scheduling strategy. This approach not only enhances the reasoning capabilities of LRMs, but also improves overall efficiency by reducing token length while maintaining high problem-solving accuracy. Ultimately, ALPHAONE addresses the need for a more dynamic and adaptable reasoning process that aligns better with human-like cognitive strategies.
How does the proposed ALPHAONE method work? Illustrate its methodology step by step.
The proposed ALPHAONE method works by implementing a universal reasoning progress modulation framework for large reasoning models, LRMs, at test time. First, it introduces the concept of the alpha moment, where the thinking phase is scaled by a factor of alpha greater than 1, allowing for a longer reasoning process. During the pre-alpha moment, slow thinking is activated by appending the reasoning transition token, wait, after structural delimiters, NN, using a user-defined scheduling function modeled as a Bernoulli stochastic process, which determines the frequency of slow thinking transitions. After reaching the alpha moment, the method transitions to fast reasoning by replacing wait with the end of thinking token less than think greater than, effectively marking the end of the slow thinking phase. This structured approach allows ALPHAONE to continuously modulate reasoning, enhancing both the efficiency and accuracy of the LRM's problem-solving capabilities.
Can you provide a simple yet illustrative example demonstrating how ALPHAONE modulates reasoning transitions during the reasoning process?
ALPHAONE modulates reasoning transitions by utilizing a stochastic process to append the reasoning transition token wait at specific moments during the reasoning phase. For instance, it employs a Bernoulli distribution to determine the probability of appending wait after structural delimiters, with the probability, bold symbol, p_text, wait changing over time according to a user-defined scheduling function, such as linear annealing. This means that initially, the model may append wait frequently to encourage slow thinking, and as reasoning progresses, the frequency decreases, allowing for a transition to fast thinking. Once the reasoning phase reaches the designated alpha moment, any remaining wait tokens are replaced with less than think greater than to signal the end of slow thinking and prompt a shift to fast reasoning. This continuous modulation allows ALPHAONE to effectively balance slow and fast thinking throughout the reasoning process, enhancing overall reasoning efficiency and accuracy.
What are the theoretical or practical benefits of using ALPHAONE compared to existing methods such as Bayes, S1, and chain of draft?
ALPHAONE offers several theoretical and practical benefits over existing methods like Bayes, S1, and chain of draft. Firstly, ALPHAONE consistently yields higher problem-solving accuracy across all models and benchmarks, with an average accuracy boost of +3, 12% over chain of draft and +4, 62% over S1, while also reducing the average token length by nearly 14%. Secondly, it achieves more efficient reasoning by modulating slow thinking continuously, which allows for both sparse and dense modulation strategies, unlike S1 and chain of draft that only explore limited modulation. Additionally, ALPHAONE effectively addresses slow thinking inertia by implementing a post-alpha moment modulation that encourages a transition back to fast thinking, which is crucial for maintaining reasoning efficiency. Lastly, the framework's ability to scale the thinking phase budget and optimize slow thinking scheduling provides a more flexible and effective approach to reasoning compared to the static strategies employed by the baseline methods.
How is the performance of ALPHAONE validated across different benchmarks, and what metrics are used to assess its effectiveness?
The performance of ALPHAONE is validated through systematic evaluations across 6 reasoning benchmarks, which include mathematical reasoning, AMY 2024, Minerva Math, code generation, LiveCodeBench, and scientific problems, OlympiadBench. The effectiveness of ALPHAONE is assessed using metrics such as problem-solving accuracy, reported as average pass at 1%, and the average number of generated tokens. The results indicate that ALPHAONE consistently yields higher problem-solving accuracy compared to baseline methods, with a notable improvement of +6.15% accuracy for the 1.5B LRM while reducing token length by nearly 14%. Additionally, ALPHAONE demonstrates superior efficiency, achieving a balance between reasoning performance and efficiency as indicated by the Reasoning Efficiency Performance (REP) metric, which shows higher representative values compared to other methods like S1 and chain of draft. Overall, these evaluations highlight ALPHAONE's capability to enhance reasoning performance while maintaining efficiency across diverse reasoning tasks.
What limitations or drawbacks does ALPHAONE have, particularly in relation to its modulation approach and reasoning phase management?
ALPHAONE's modulation approach has notable limitations, particularly regarding the management of the reasoning phase. One significant drawback is the potential for slow thinking inertia, which can occur after extensive slow reasoning, making it challenging for the model to transition back to fast thinking effectively. This inertia can lead to a prolonged reasoning phase that may not yield optimal results, as evidenced by the observation that simply inserting a few less than think greater than tokens does not adequately counteract this effect. Additionally, while ALPHAONE aims to modulate reasoning continuously, the need for careful selection of the frequency of slow-thinking transitions, parameterized by p_text constant, indicates that both extremely low and high frequencies can result in subpar performance. Lastly, the framework's reliance on a user-specified scheduling function for slow-thinking activation may limit its adaptability across diverse reasoning tasks, as the optimal scheduling strategy can vary significantly depending on the context.